Okay, so as you know, you have a midterm on Saturday, and today we will have some review session on binary classification and multi-class classification, and we will look into the accuracy metrics, the performance of the models, and we will see uh, some comparison of the models and understand uh, which model to select based on the accuracies. So I've already uploaded the IPython notebook files on Moodle. You can find them named as PSS9 binary classification and multi-class, and we will use the breast cancer dataset in the binary classification review part. So you can either download the dataset from the Moodle, or you can download it from the Kaggle. So, so the breast cancer dataset itself represents some observations of the human breast cancer, and it includes information about the breast, about the cancer radius, some texture, perimeter, some uh, some medical indicators that are used and that are important for deciding whether the cancer is benign or malignant, in which malignant means Charag in Armenian and benign is Barag. So here we load the dataset, and preliminarily I knew that there is one unnamed 32 column in our dataset, which was the extra indexing column in it. So I automatically dropped it while loaded the CSV using the pandas read CSV module. And as you can see, we have some numeric variables in our features, and we have a response variable that is actually the diagnosis of the patient having malignant or benign cancer. And the rest of the features contain numeric values. There are some smoothness worst, compactness worst, concavity worst, I don't know, different measurements that that the doctors probably take into consideration while they decide whether the cancer is benign or malignant. So our task in here, as you can understand, is to uh, construct a classification model which we will use to predict the classes of diagnosis vector. So while we print the information about the data set, we can see that we have some float values in our feature set, and we have a diagnosis as an object which contains M and B values that are actually string values. So to make sure that we have exactly two unique classes in our diagnosis vector, we use the breast cancer that diagnosis vector that is actually one column of the data set that contains the values of diagnosis, and we convert it to a NumPy array vector, and we use np.unique to understand how many different classes are present in our response variable. So So we have one categorical variable in here, and you might have already learned from the um, regression classes that we can either map those values into, for example, 0 or 1, or we can use the get dummies method to convert the categorical variables into numeric. Here I introduce another uh, good method to convert the categorical variables into numeric. I use the labor encoder in here that is from scikit-learn preprocessing library. And here we initialize an object of labor encoder class, and we just use the uh, fit transform method on the categorical label encoder object to transform the breast cancer data diagnosis vector into the numeric values. And here we automatically assign the already fit transform vector into the breast cancer diagnosis field. So now you can see that it will print the unique number of classes present in the already transformed breast cancer data diagnosis vector. We can see that we have 0 and 1 as transformed variables for the benign and malignant diagnosis. So M in here is 1, and B represents the 0. So now we have a fully numeric values in our data set, and our task is to construct a classification model. This is for you just to understand how the features are interacted together. We use Sabre library in here to like plot some random two features in the same coordinate plane. And for example, we can see that uh, the plot radius mean versus the fractal dimension war has the following form, and we can see that uh, by eye, of course, that there might be some separation, and the separation um, can be considered as part of the classification model. So we can see that we have two distinct classes in here, and we can somehow identify some boundary in here that mm, for our understanding uh, to see that we can separate those two classes. I mean, not classes, but two observations that correspond to two different classes. So in here we assign X to X the breast cancer data without the diagnosis feature, and Y is our response variable that contains the diagnosis values of the breast cancer data. And we have in here 569 observations in our X, in which we have 30 number of columns that represent the features, and we have 569 observations in our label set, which corresponds to the row dimension of the X matrix. So, do you have any questions?
Yes, sorry.
Okay.
Are classes linearly separated?
Uh, can you repeat the question, please?
Are those classes linearly separated?
Uh, I mean, there can be a linear separation between those classes, uh, and as you learn the linear models to separate the two classes within the scope of your classification models, yes, we can use the linear separation in here. But this is just two random vectors from our data set that are plotted together. We can use some, for example, different, for example, area mean in here. Sorry, let me load the data in here. Okay, we can use, for example, the area mean to see if we can identify some separation. And here we can use, for example, the texture mean, the area mean versus the texture mean. And this is just for the visual understanding. We cannot actually plot the whole feature set versus each other because that would be really huge. But we will try to understand how our logistic regression in here tries to overcome the task. So I have provided another notebook in here which contained the, an example of logistic regression with k-fold cross-validation and regularization. And if you open that, you might already know that we have some C parameter in our, we can have some C parameter in our logistic regression model that is actually the inverse of the C parameter is inversely proportional to the lambda in our regularization model. And as you remember, you used ridge and lasso regression, ridge and lasso regularizations while trying to predict the response variable using the linear regression model. And here also we have the concept of regularization, and the idea is pretty the same. The regularization tries to regularize the number of model parameters in here, the betas, and for that we should somehow determine the value of lambda. And for that we use the train test split from the scikit-learn library model selection, and we split our dataset into training and testing separate datasets in which the size of the trained data actually is the 80% of the X matrix, and the rest that is left to the test set contains the 20% of the actual values of X. So we have some new four matrices in here, and and while we print the shape of our feature matrix, we have 455 over 30 dimensional matrix in our train set, and we have 114 in our testing set, and corresponding label vectors also. So in order to estimate the optimal value of C, that is actually equal to 1 over lambda in the regularization model, we initialize some default C values in the form of, for example, list or numpy array, and we use the powers of, for example, 10, and we try to estimate the model performance based on the values for each values used in the logistic regression model. So While iterating over all values in the C, we try to construct a logistic regression model. And for example, we use the L2 regularization, that is the ridge one. And we use C as the val in here. And every time the value changes with respect to each items in this list. And we try to estimate the performance of the general idea is to estimate the performance of our LR model for each C and understand the value of optimal C for which the accuracy is the maximum. And by talking about the accuracy, we uh, we want to use the cross validation, the k-fold cross validation in here, and that's why we initialize an object of k-fold for the k-fold class, in which the number of splits is equal to 10. This is just a default value, you can change it. And we try to estimate the scores of our model while using the k-fold cross validation on the train, X train and Y train, and the scoring is accuracy in here. So uh, you already might have guessed that the score in here is actually a list. So cross-validation score in here provides the accuracy score for each fold used to estimate the accuracy. So, and here score would be a list containing 10 accuracy scores. And at the end, we append this result into the score result, logistic regression list, and we just print in here the value and the average of the tenfold cross-validation scores for each C. So while we print it in here, we can see that for C equal to 0, 0, 0, 1, the average cross-validation score is 0.92. And for each of the value of C, we estimate the average cross-validation score and obviously take the C that corresponds to the maximum average cross-validation score. That is the average accuracy of the cross-validations. So in here, you can see that C equal to 1000 is the value that provides 0.9605, etc. accuracy, that is the highest among all the C values. So we can take the value of C equal to 1000 as our optimal value in here, and we can to see how to see the relation of C values with the cross-validation average score, we can use the matplotlib in here to plot the C values on the x-axis and the accuracies on the y-axis, and to see for which C value we have the maximum accuracy. And this curve actually in here is quite flat. Just a second. It's quite flat because the C values in here are pretty close, and the plotting library could not make it more visible. But we can take we know that the optimal value of C is 1000, and we can take the value of the index of the value maximum score by using the np-argmax of the arg series scores that will return the index of the maximum element in the average cross-validation score list in here, in here, and we can just take the index, the element corresponding to that index from the cprom list. And this is the same as the 1000 as we saw a little bit above. And you remember that the value of c is actually the inverse of the 1 over lambda, and lambda is equal to 1 over c. So and here the value of lambda is equal to 1 over 1000. So the question was, why do we take that values from C prime? This will be incorrect if we choose some. No, that would be also good. So yes, we can generate the values for C using the numpy or some range. And as already we know the optimal value of C in here. Okay, thank you too. As we already know the optimal value of sin here, we build our logistic regression model using the so here should be 1000, using the 1000 as our C parameter, and we fit our model into X and Y, and we use the predict problem methods to get the probabilities of the observations and those classes. And in here, we just plot the confusion matrix using Y, that is the actual labels in our data set, and the Y pred LR, that are the uh, predicted labels in our data set. Now, as we can see, uh, we have pretty high scores in our diagonal that represents two positive and two negative weights in our data set. And we can see that our model was quite good at classifying the observations that actually corresponded to class 0 and predicted as class 0. And we can see that our model was pretty good at classifying the observations that corresponded to class 1, and it was able to classify them as 1. And we can see some force in here, which indicate that in 4 cases the label of our observation was 1 and our prediction was 4, and vice versa. But to deeply understand and we can see some balance right in here between the true negatives and false positive rates in our model. And we can see that we don't have some high value in here and a low value in here and vice versa. So our model was able to classify some values with some precision, and it didn't give some priority to the class to the observations belonging to class 1 or the vice versa. So we have some balanced misclassification rate in here. And while looking at the classification report, we can see that our model was pretty good at classifying both 0 and 1, and we have some good precision score in here, and the recall score, and the weighted average of the precision recall. I mean, not the average, but 2 times precision times recall over the precision plus recall score was pretty high, and we have pretty high precision score for the class 1 also. And while we use the ROC curve in here to understand the false positive rates and the true positive rates and the thresholds of our model that corresponds to the label 0, we use the ROC curve and the predict pred probabilities in here, and we calculate the area under the curves to see the overall performance of our model, and of course to plot the ROC curve and the precision curve in here. The idea is just the same as we did during our PSS sessions like last and the 2 weeks ago. And we can see that the area under the curve corresponding to class 0 and of course corresponding to class 1 are pretty high, and the precision recall AUCs are also pretty high. And while we're plotting here the ROC curve and the precision recall curves side by side, we can see that the false positive rate versus true positive rate is quite the curve is quite a good one. And as you remember, this is a probability curve that represents the false positive rate versus true positive rate for each threshold that our model is uses. And we also look at the PR curve to understand whether we might have some, for example, class imbalance problem in here, or we might have some problems with the trade-off between precision and recall. And we can see that both the precision and recall are in a good trade-off in this curve for each class. And as the precision is the intuitive ability of our classifier not to label as positive a sample that is negative, our model is good. And as the recall is the ability of our model to find all positive samples, we can see that both performance metrics are high, and the AUC, as you have already seen, was also high. And we can conclude that the logistic regression could successfully tackle the task, and it provided some pretty good results on classifying the breast cancer labels in a binary classification problem. And I believe we had some the data observation count in here is 569, which is actually not so big number for having pretty accurate results in the classification models. But as you see, maybe the data was a good one, maybe the model was capable of classifying all the labels. We can see that we have pretty good accuracy scores in here, and logistic regression was capable of classifying those labels successfully. So I will stop recording.